How is it actually possible that with coroutines we are able to write code that can be suspended and resumed at a later point in time? It seems a bit like magic, right? In this lecture, we are now going to take a look at the internal workings of the Kotlin compiler to see what's actually happening under the hood. You will find out that no real magic is involved and everything can be explained. Keep in mind, however, that I'm going to simplify a lot here. I personally don't think that you necessarily need to know all the details of the internal workings in order to write solid code with coroutines. However, a basic understanding about what's going on behind the scenes can help you in understanding coroutines at a deeper level. This, in turn, will help you to write even better code. Let's first have a high-level look at how the build process works for Android applications that are written in Kotlin. We write our Kotlin code in files with the extension .kt. As you know, Kotlin is a compiled language. This means that before you can run code written in Kotlin, you first need to compile it. The Kotlin compiler therefore compiles all the .kt files to class files. The code in these class files is also called JVM bytecode. The Android build process is very complex and not relevant for our purposes. Therefore, I'm going to simplify it a lot. So the Android build process takes the generated class files and packages them together with other resources into a final APK file that can be executed on Android devices. The most interesting work for coroutines is done in the first part, when the Kotlin compiler compiles Kotlin code into bytecode. So let's take a closer look at this part of the build process. The Kotlin compiler takes code from Kotlin files that looks something like this and generates bytecode that looks something like this. You can take a look at the resulting bytecode directly from within Android Studio. So let's jump into Android Studio. So here we have a simple main function that prints out Hello World. And by clicking on Tools, Kotlin, Show Kotlin bytecode, you can see the resulting bytecode on the right pane. We can also decompile this bytecode back to Java code by clicking on Decompile. Now we see the Java equivalent of the bytecode. This is helpful because it makes the bytecode easier to understand, and so it makes it also easier to figure out what kind of code transformations the compiler actually performs. When it comes to coroutine and suspend functions, the compiler does some really sophisticated code transformations. Let's take our simple suspend function from our last lectures. It prints out when it starts and finishes some work. This work is represented by calling the delay function. When compiling this suspend function, the Kotlin compiler transforms the code you can see here into bytecode. If we would decompile the bytecode then back to Java or Kotlin code, we see the transformations that the compiler actually applied. For our example here, a simplified version of the decompiled bytecode would look like this. So the compiler performed the following code transformations. First, the suspend modifier got removed, so in the bytecode, our function is just a regular one. The compiler also added an extra parameter to the function signature of type continuation. The body now contains a when expression. Depending on the label property of the continuation object, either the first string is printed and delay is called, or the second string is printed and continuation.resume is invoked in order to communicate back to the caller of this function that it completed. I simplified this resulting code a lot. In the real world, it is more complex, but for our purposes, I think this level of abstraction is appropriate. The mechanism that you see here allows suspend functions to be executed only partially. The continuation parameter on the one hand acts as a callback, in a sense that it notifies the caller when it has completed by invoking continuation.resume. On the other hand, the continuation object also acts as a state machine, because the state of the execution, like for instance the label, is stored in it. So let's recap. No magic is involved when using coroutines. Most of the sophisticated functionality of coroutines is achieved by clever compiler transformations. The compiler transforms suspend functions into regular functions that receive an additional continuation object. Depending on the state of the continuation, different code of the suspend function is executed. This clever mechanism allows a coroutine to be split up into separately running code blocks. I hope I could convey some basic ideas about how the compiler achieves the behavior of coroutines. If you want to dig deeper, you can check out the link I added to the resources, where Roman Elizarov from JetBrains, the lead designer of Kotlin coroutines, explains in great depth how coroutines work internally. So this was a free video from my online course called Mastering Kotlin Coroutines for Android Development, which contains more than 9 hours of high-quality video content and is therefore probably the most extensive and in-depth resource about coroutines on Android. If you are interested, please check out the link in the description.